So our next talk is by a company called Cloud Physics. And they'll be talking about collective intelligence for data center management.
Thanks, Andy. My name is Xiaojun Liu. I'm from Cloud Physics, and today I will give you a quick overview of what we are building as a service and our experiences with developing on Spark and running Spark in EC2, and closing with some ongoing work that we are doing in this area. So what we are building is an operations management software as a service offering. So on the left-hand side of this slide, it shows our user interface that's organized as a deck of cards. So think of each of these cards as an app on a smartphone. So it focuses on a particular aspect of a user's IT infrastructure. For example, for all the data storage devices in a user's environment, how are the spaces consumed by different kinds of files, and an expectation or prediction of in how many days, say, a data store will reach full capacity. So on the right-hand side, the top part shows among these cards, there are a subset that are pre-built by us. In this case, it shows you a card that allows you to simulate resource reservation ratios when you need to reserve certain compute resources in your cluster to deal with server failures. And then on the bottom part, it shows the way we provide a drag-and-drop user interface to allow you to easily pull together relevant data for any task, really. For example, to debug a performance issue with a virtual machine in your infrastructure. You can pull together, say, how the relevant configuration parameters of the virtual machine, which physical server this virtual machine is running on, the list of virtual disks, and all the data stores that these disks reside on, and then all the relevant performance metrics for these objects. And longer term, what we are aiming to build is really a Google Now-like service, but for data centers. For example, with Google Now, it may alert you to leave earlier to catch a flight because of a traffic condition on the way. In our case, our service can alert an administrator to be ready to provide more compute resources when a spike in resource consumption is detected. So this slide shows the backend infrastructure that we have in production right now. So on the bottom left part, the blue box represents the data collector virtual machine that our users download and deploy in their local infrastructure. So this data collector virtual machine will collect performance, configuration, many kinds of data from the user's environment and uploads it to our backend, which runs on Amazon's cloud service. And then the right-hand side shows how we organize the computation for many of the cards that we provide for our users. So this is a kind of a quick overview of the kinds of data that we collect from our users. So it includes the various configuration parameters of a user's infrastructure, like, well, for all the virtual machines, how many virtual CPUs are configured, what's the provisioned memory size, et cetera. And then performance metrics, tasks, think of these as a structured form of log data from a user's environment. And then we collect data from all kinds of objects, including virtual machines, physical servers, network switches, both physical and virtual, and storage devices. So at this time, I think our service became generally available about 3 months ago in late August. And from the current active user base, we are collecting over 100 billion performance data samples per day. And on an average data center in our data set, we collect over 1.3 million properties that describes all the objects in a user's environment. So what motivated us to look into Spark and related frameworks is our need to analyze this data we collect from the users to detect common patterns in the data set, so we can say at a time when a new feature is released by, say, a virtualization product vendor, and when we detect performance issues when certain subset of our users make the feature upgrade, then we can alert other users, say, to hold on until potential issues with the upgrade is resolved. So we started to build a cross-user analysis framework built on Spark from a few months ago. And this is a kind of a high-level diagram of our current setup. On the right-hand side, the data repository is kind of the canonical copy of all the data that we collect from our users across history. And then we have what we call a history table in the HBase cluster that contains kind of the metadata for the data we collect. That includes say, the organization ID, the ID of the data source, timestamp of the data collection, type of the data, et cetera. And then the table contains pointers to the S3 objects for data retrieval. And then we have a status server that's built on the Play framework that responds to kind of a metadata queries. For example, you can ask with a certain data range for a particular user and its data center, what are the list of, say, the configuration snapshots that we collected from that user. And then on the left-hand side, right now, all of our analysis code is built as a standalone app in Scala. And it uses a library that we built for Spark called Tesla that has functionality to provide data queries. So you can ask for, say, data we collected from all users in a certain date range. And then utility functions to extract relevant properties for virtual machines hosts for further analysis, or the relevant performance data metrics. And then utilities to segment the data, for example, to divide our user base into different buckets based on like how many running virtual machines or hosts that they have. And then here is a short list of some of the analysis that we have done with this framework. For example, we have looked at among our users' data set, what are the virtual machine configured resources in terms of CPU, memory, and storage, and then the utilization level of these resources. Similarly, for servers, CPU and memory utilization distribution. For storage devices, what are the popular storage vendors and interconnects that are present in our user community. And then also some analysis of the product features from virtualization technology vendors, how widely they are adopted in our user community. So right now, most of the results of this analysis feeds into our internal product planning process. For example, let's say if we are planning to develop a card that works with a particular product feature, let's say VMware's high availability feature, then we can look at our user set user data set to figure out, okay, if we develop this feature, then, well, how many users in our community will benefit from such a feature? So here is just a quick snapshot of one analysis that we did in terms of virtual machine CPU and memory size distribution in our data set. This represents, I think, from a subset of our users with over 100,000 virtual machines. So as you can see, most of the virtual machines are clustered between 1 to 4 virtual CPUs and 1 to 8 gigabytes of virtual memory. But there is a wide distribution of both in terms of virtual CPU count and virtual memory size. So here's just a quick summary of our experience so far working with Spark and related frameworks. So it's fairly quick for us to getting up to speed. And also, most of our backend components are developed with Scala. So Spark is, for us, is easily integrated as another piece in the puzzle. And then all of our production systems runs in Amazon's cloud service. And also in our internal DevOps process, we use Ansible. So the Python scripts that launches Spark clusters in EC2 had worked very well for us, and it's easily integrated into our internal DevOps workflow. And then the Spark runtime actually tolerates the variations in task execution time fairly well. So for some of our analysis, there are stages where the runtime of the tasks is proportional to the size of our users' infrastructure. So the sizes, in our case, can vary by over two orders of magnitude. So from a few servers and dozens of virtual machines in a small IT shop to hundreds of servers and thousands of virtual machines in enterprise data centers. So because the Spark executor will pull a remaining task once it finishes a task in the current stage, so this actually distributes the load among executors fairly well. One downside that we have observed is actually a generic issue with EC2. So we often observe fairly large variation in EC2 instance performance. Sometimes in a fairly small cluster, like 8 or 10 machines, for similar tasks, the execution time can vary by 2 to 3 times. But this is widely reported, and there are publicized methods to work around this. So here is a quick summary of the kind of the tasks that we're planning to work on in this area. So we are going to create an API for the frequently used analysis that we have already created. So make it easy to update results over time and make the consumption by other members in the team easier. And then right now, for some of our analysis, we actually use a few Spark jobs to extract and summarize the relevant data, and then dump the results into several CSV files, and then use R or Python scripts for further processing. So we are looking into Spark and Shark and MLlib to rewrite these analysis jobs. And the next one is really the most interesting kind of technical challenge in our mind right now, is to use Spark streaming for near real-time performance data analysis. So in our case, the use cases include trending of resource consumption for capacity planning purposes, or to detect resource bottlenecks to optimize placement, say, virtual machines on physical hosts or virtual disks on storage devices. So, but given the incoming data volume, so this is a big challenge for us right now. And we are just starting to evaluate the various options to encode or compress the performance metric data. So the goal being to keep a larger window of data in memory. So, well, in closing, so our kind of journey to adopt Spark and related frameworks is still early. We are looking forward to learn more from this vibrant community and contributing back. Thank you.